Okay, I think everyone online should be able to hear me. Let us remind ourselves what we're doing. I guess there's this SPOT survey thing. It stands for, apparently stands for Students' Perspective on Teaching. So it is a survey to get your perspective on teaching. And they ask us to give you 15 minutes at the start of class to do this. But given that most people watch this online anyways, I don't think that's a good use of time. So I don't know, I guess if you watch this online, just do the survey at some point. It tells future instructors, and I guess myself if I were to teach this course again, what to improve. And I get to read what you write in an anonymous way. So that's kind of fun. So anyways, do that if you want to give some feedback. It's completely your choice. But I guess it won't hurt. Okay, so that's the survey. And now let us actually remind ourselves what we're doing in this class, which is we're trying to solve this classification problem, right? Which is different from regression in the way that the thing you need to predict is somehow this discrete set of objects, like the type of wine or what's in a photo or something like that. And last class, we covered how you might solve this problem for the case where there's two classes. And since there's two classes, usually two things is called the binary. And so it was binary classification. And maybe before we remind ourselves how that worked, we can think of, like, roughly speaking as a human, how we would do this, and then see how that maps to what we found out last time. So the way you think about this is, like, you're a human, you know, and you've seen a lot of photos of things in your life, and you've been told what, like, I don't know, photos are of things. Like, you'll be like, oh, you can probably identify a cat and a dog, and sometimes it's not that obvious, and so on. And so you can imagine, like, you know, someone comes up to you on the street, and they're like, listen up, I've got this photo for you here. Can you please tell me what you think is in the photo? And maybe it's like a picture of a car, and they're like, tell me which company made this car? Like, what model is the car? Is it like a Toyota or a Ford or something like this? And so maybe the first question they ask you is like, is this a Toyota? Right? So it's like a right or wrong question. You look at this thing and you're like, okay, I know something about cars, and some people will know more about cars than others based on how much, you know, cars they probably saw in the past, which is like the data you saw in the past. And then you'll probably in your mind, I don't know, be like, okay, you know, maybe it's like 70% chance I think it's a Toyota, and then like 30% chance it's something else. And then they're like, okay, like, I need you to give me what's the label? I don't care about your percentages, you know? And then you'll be like, okay, I should probably pick the one that's the more likely one of the two, you know, the one that's higher than 50%. That would be the 70% one. And so you'd be like, okay, I think this is a Toyota, probably. And this is sort of what our algorithm is actually doing, our learner, right? It gathers all this data, which is like maybe all the pictures you've seen in your life. And then we produce this predictor, and then we're asked to predict new, like, on new examples. And this is like someone coming up to you on the street and asking you, what is this photo? And the procedure we came up with last time is essentially just learn the probability of whether you think it's right or wrong, yes or no, or whatever. And then when you're asked a new question, be like, well, let's look at the probabilities. And if it's greater than 50%, let me predict yes, and then otherwise predict 0. That was essentially all we did. And the difficulty was to come up with how do you learn what the probability of a new photo should be. And then we saw that, roughly speaking, well, the probability is just like this continuous number between 0 and 1. And we know how to solve for, you know, predicting continuous numbers. That was just like a regression problem. And so we found out that one way to think about this is you solve a regression problem where you predict the probability of getting 1, or the probability of predicting here a Toyota for this class. And then you just look, is this greater than 50%? And if so, I predict yes or 1, and then otherwise I predict 0. That was the story. Mathematically, the story went like this. We said that, the function f Bayes that predicts the best on new data turns out to have a special form when we care about this binary classification set. Well, actually, when we care about classification in general, it has the form that will calculate the probability of getting of every label, giving your new example, your new photo in this case, and then just pick the argmax one, the one with the largest probability. And in the case where there was only two options, that's just pick the one with greater than 50% probability. In the case where the person asks you to identify, like, give me the model, not if it's Toyota or not, well, then you'd be like, okay, let me first remember all the models of cars I know. That's maybe the number of classes in this problem. And then you'd be like, maybe roughly you can, you know, if asked, you'd assign some sort of probabilities to each of them, and then you'd pick the one with that's maybe that has the highest probability. And that's what this is doing. And then we studied this binary case, as we said. And then what we noted is that all we need to do is learn this PMF, which is we just need to learn the probability of each class. And the simplest way to start was, let's just consider two classes. In that case, all you do is learn the probability of one class. Then from that, you can infer the probability of the other class, because it's just 1 minus it. So we just need to learn the probability of class 1. In other words, you can just, this type of PMF is called the Bernoulli distribution, where there's a parameter just describing the probability of getting class 1. Okay, we went through, and then all that was left was to calculate this parameter. Then you just work out a bunch of math, doing maximum likelihood estimation as a procedure to calculate the parameter that is the most likely given the data we actually observed. And if the data changes, you know, your parameter changes. That's like if you take two different people, if they saw, you know, if they lived in different countries, maybe they saw one model of car more than another, they might have different predictions. Okay, so we did that whole procedure, and we arrived at that the maximum likelihood estimate was just, where was it? We needed to estimate this parameter here. Okay, then we're like, okay, we need to solve this equation to 0, but we couldn't do that, so then we just did gradient descent to get an approximation to the solution to this this problem here, which is, sorry, we wanted to solve this problem, which is to minimize the negative log likelihood. And so we did this through gradient descent. And yeah, and so after you run gradient descent, you should get something close to the maximum likelihood estimate. What you do is then take that estimate, you plug it in to your function, which will estimate the probability of getting 1 or 0. That's our estimate of alpha star, the parameter describing the Bernoulli parameter, which is the probability of getting 1. It was just, we assumed it has this form, which is a sigmoid applied to a linear function, where the parameter or the weights of the linear function we didn't know, and then the maximum likelihood estimation procedure just gave us a way to get an estimate of W star. Okay, and then these are approximately equal, and yeah, this is the probability of getting 1. That is our estimate of the probability of getting 1 if you input some new feature, some new picture in the example. And so that's our estimate of F Bayes. That's how we're going to predict things. We're going to say that our binary predictor for some new feature is simply taking the class that maximizes the following. And since this is binary classification, if we plugged in the definition of this, we saw that you can think of it, it's just the case where this sigmoid function is greater than 50%. Or in other words, the probability of predicting 1 is greater than 50%. And then if you look at the way the sigmoid is defined visually, you find, well, when is the probability greater than 50%? Well, that's over here. So that's that case. And then when is it less? It's over here. And then you look, okay, so that's when the input to the sigmoid or the logistic function is positive, you predict 1. When it's negative, you predict 0, because it's below and above 50%. Okay. And we saw that, roughly speaking, visually, you can think of this as like what is called a decision boundary. So it defines a boundary. This is your predictor. Your predictor can be viewed as a boundary, where above this boundary you predict one class and below it you predict a different class. And in this case, if x's are zeros, so y equal to 0 case, then your decision boundary will likely look something like this, where everything over here has a prediction of 0. And everything over here has a prediction of 1. In other words, your probability, the probability you think of getting, if you get some input x, right, which is just a combination of these two features, if it's in this region, the probability that you think it's 0, the probability you think it's 0 is greater than 50% here. And the probability you think it's 1 is greater than 50% down here. That's it. Yeah, okay. And yeah, like we did all this for like the linear function in the sigmoid. You can replace that with polynomial features. You can also add this map stuff to get something with that gives regularization as in your objective as well. Okay. And then it turns out that we were able to view this whole procedure, as we had said, as just solving a regression problem to estimate the probability of getting one, and then afterwards just picking the class that has the largest probability, or checking if this probability is greater than 50% and predicting one, if so. Okay. And the way this was formulated, I guess there was one thing I wanted to mention, is it was formulated as a regression problem through this like ERM procedure. And there, I needed to define a loss in the predictor. And so our predictor is just this sigmoid of x transpose w, which was the function we used to represent the probability of getting the class 1, which makes complete sense because here we're trying to predict the probability of class 1. And then the loss is just that objective that we ended up getting to when we did the maximum likelihood estimation derivation. And it looked like this. Okay. And this has a name, which is something I wanted to mention. So this is in machine learning world, people will just say, let's just do classification where we use the binary cross entropy loss. Okay, so this is the binary cross entropy loss. And if you were to have, I could have just directly told you, okay, we're going to do classification by minimizing this loss, predicting the probability of 1, and then outputting 1 if it's greater than 50%, and otherwise outputting 0. But we went through this maximum likelihood approach, which is maybe somehow more intuitive or has a nicer story than me just telling you that let's use this loss and solve this regression problem first. Okay, and let's see. Well, we can also interpret the loss, I suppose, which is like if y is equal to, so your data is going to be like ones or zeros, right? It's like whether you got class 1 or 0. So if y is 1, well, then you get like -1 over here, and then here you get 0. And in the case where y is 0, you end up with this term being 0 and this one being 1. So we just need to consider two cases. You can see that for each case, it's just going to be, the loss is going to be either this or like this term. Okay. And then the question is like, what does it mean? Well, okay, in the case where y is 1, you end up with like this term here. And then you should be predicting 1 in that case. And log of 1, if you remember, is 0, right? And if you predict anything else, you're going to get a log. So you need to predict like a number that's between 0 and 1. If you predict something less, that's going to give you a negative number. Log of a number less than 1 is going to give you a negative number. Because like e to the negative power is going to give you a number less than 1. And so what you will end up with is negative times a negative number here, which will be a positive loss. So basically, in the case where the class is indeed 1, the way to minimize this is to make this quantity equal to 0, because that's the smallest that the log can be. So you want to set this to 1, which just checks out. You want to the way to minimize the loss for the case where the class is 1 is to predict 1. If you predict anything else, your loss is greater than 0 or larger than 0, and you get punished. In the other case where the class is 0, you end up with this term because you end up with 1 minus 0 here. And then how do you make this as small as possible? Well, to make this as small as possible, you're going to want to, it turns out if you look at this again in the same way, you're going to want to make this prediction 0. Then you get log of 1 and you get log of 0. Okay, that's the story. And if you make it anything else, you're going to end up with a log of a number less than 1, which will give you a negative number. And maybe this should be a minus. Let's see. So we got the loss from here. Oh, yeah. So where is it? So we did this maximum likelihood estimation. We ended up to over here. And then it turns out I forgot how to expand a minus sign. And this minus sign got applied to here, but it didn't get applied to here. So this should have been a minus, which checks out because then this explanation was not working, as you could see. So this should be a minus. Okay. Oh, well, I guess this is a minus because I have brackets around the whole thing. So we're all good. Okay, great. So in other words, this quantity has like a minus from this thing. And yeah, this quantity, unless you predict 0 here, is going to be a negative number. And then it's going to be a negative times a negative. So it's going to be a positive loss. Okay, good. And that's the binary cross entropy loss. Great. Okay, all that was left to say before we move on to the multi-class case where there's multiple labels, or there's multiple choices for the labels other than just 1 or 0, is to just, there's sometimes this question of like, why not just learn, the probability of 1 using linear regression, which you could do, and just use this linear function if you recall. So just use this instead of using this sigmoid thing. And I mean, you could go ahead and do it, but just like all we're going to do is just see like a visual kind of example of why this might not be such a good idea. And the issue comes up that like it's very sensitive to outliers, okay, in your data. That's going to be the idea. And so let's just interpret this, and then there's another plot below here. Okay. So you get these data points, and you either, so this is 0, this is labeled 0, and okay, so you have one feature, just one dimensional. And yeah, so there's a bunch of values of this x, and then you ask, what is the label for this x? And you get some data points. These are these black points. So you end up with, I don't know, here there's like something like 14 data points. And so you get a bunch of 0, 0, 0, 0 here, and then 0, and then 1, 1, 1. So you can see this kind of trend that it seems that around this region, when x transitions, like after here, it seems to change to 1, the label, and then before that, it's kind of the label is 0. Okay, that's maybe very reasonable for some sort of problem. And the way your prediction works, right, is that you predict the probability of getting 1, and then if it's greater than 50%, you'll output 1. So maybe the sigmoid, that's your prediction of 1, will look like this in this case. So this is after you've already solved the problem. Maybe it'll look like this, and you would see that at this point, right, so this is the 50% point. This is where your prediction is 50%, and afterwards you're going to predict 1. So the sigmoid after this point here has a value of greater than 50%, and so to the right you would predict 1, which makes kind of logical sense. This might be the boundary you come up with. And maybe in this case also the line, which you would use instead. So if you did linear regression, you would use this linear function to predict the probability of 1. And then you would say, oh, my line, when it is greater than 50%, which is anywhere here, and then afterwards, even when it's greater than 1, you're still going to somehow interpret this as a probability, you'll predict 1. Okay, so everything to the right, and maybe in this case it's reasonable, and actually you might get a line is the like a line might of this form might actually minimize remember the error. And so what does the error look like in this case? It would have been the squared distances, right, of the line. This is what it was. Okay, good. And yeah, and so this is doing linear regression with like the squared loss with this line. And with this purple guy, this is the sigmoid function, you were doing this regression problem as well, but you were using the logistic or the sigmoid function, so we call this logistic regression, and there you were using this binary cross entropy loss. Okay, and so now what happens if you introduce just one new data point, which is like an outlier, in the sense that like, given this trend, it seems like any large value of x will produce a value of 1. So this is maybe an outlier, but it's also not that unreasonable. Like there's just a really large number of value of x. It's probably going to be labeled 1. Well, now what's going to happen, right, is that this sigmoid function, well, it's still going to keep going, and it's just going to approach closer and closer to 1. And this will basically give you 0 error, and it's not really going to change your prediction much, right? You're not really going to suffer anything based on this point. However, for the linear function, if you're using the squared loss, you can just imagine how much error there's going to be if this was your prediction between this and this distance. So the squared loss will be enormous. Okay. And so for that reason, you're going to end up with this line being heavily skewed to the right, like being tilted, and so that this error is not so large anymore, because otherwise If it stayed like this point would have suffered an enormous amount of error. Okay, so the line that minimizes this data set now looks like this. And the unfortunate thing is that this becomes heavily skewed to the right. And so the point at which it's now greater than 50% probability is after this point. And so you would predict 1 here and 0 here. And just like visually speaking, you can see that that's probably not as good as the boundary that's here. Because you end up mislabeling a bunch of points that probably should be 1 in this region. Okay, so that's kind of the just high-level idea of why the squared loss with the linear functions is not the best idea. But people, I mean, you could still try it and use it, and sometimes it'll be okay. Okay, that's the end of that. Let's go into this multi-class business now. So how does this multi-class classification stuff work? Well, the way it works is that we just have multiple classes. Multi-class classification. And somehow this is probably mathematically the most tedious and difficult lecture of all the lectures. And I feel like in part that's reasonable because we end up with all these classes and we end up needing to solve for like an estimate of the probability of each class. And so you end up with like, you know, we're going to end up with K predictors, kind of. But also upon review, I feel like, you know, part of it is probably due to poor notation choice by me. And I was a little too lazy to fix that in any reasonable way that I could come up with. So we're going to have to deal with the notation I chose to do last year. So if you get bogged down with the notation and you feel like it could be done better, you're probably right. Okay, so just keep that in mind. But it never hurts to you know, struggle a little bit. Okay, so let's try this. So how is this going to work? Well, let's just remind ourselves what we're trying to do here. If we go back to the binary classification business, we started the whole story with, oh, we need to we have this property. So let me just take that. And so we just need to learn this PMF. And so we're just going to do that for the multi-class case. So we started with this. We're like, oh, okay, let's learn this. Let's learn this PMF. But now we have multiple classes. We're going to have K classes. And we're going to start indexing from 0 so that it nicely matches in the binary case. So there's 0, 1, 2, 3, up to K minus 1. There's a total of K classes. Before we considered K equal to 1, or sorry, to 2, which was 0, and then 1, or sorry, 2 minus 1, which was 1. Okay. So how is this going to work? Well, it's going to work the same way as before, which is we're going to use MLE, maximum likelihood estimation, to estimate the PMF P of y given x. And this is a PMF because the labels are this discrete set of objects. Okay. And then how does that work? Well, the way it works is you have this data set, and maybe I'll write it just for. So you get this data set. Whoops. You get this data set. Remember, it looks of this form. It's like, oh, these, you know, xi, well, x1, y1 up to xn, yn, guys. And each one of these is IID. From some distribution P of xy. Okay, good. And okay. The reason I write this is because, yes, there's this distribution, and also there's like these conditional distributions. So there's also this guy here, which is like P of y given x. And that's the thing we want to learn. And the question is, like, what do we choose for this? What are we going to assume it is? Before, we assumed it was this Bernoulli distribution because there was only 2 classes. And that really was without loss of any generality because, like, there's only 2 classes. There's only some, like, one probability of one and one probability of the other. There's no other possible distribution you could imagine it was going to be. And so the question is, what are we going to assume for multiple classes? Well, what we're going to assume is, like, the obvious thing, which is also without any loss of generality, which is people come up with names for these distributions, but like essentially if there's k classes, we're just gonna have a parameter that describes the probability of each class. And then instead of just saying that this is like a function that maps, every class to a number or probability, people give this a name, just like the Bernoulli, and this is called the categorical distribution. So a categorical distribution is just going to be a distribution when you have k discrete things. Okay, how does that work? Well, it works like this. So we assume, maybe I shouldn't put assume. Okay, so this like random variable, each one of these yi's given xi, we've seen this before. We're going to assume it's coming from a categorical distribution. And we have sort of briefly seen this in the probability chapter, and now it's coming up. And the way this works is there's as many outcomes as there is in your random variable, right? Is the number of parameters there are. And so since we have k outcomes, we're going to have k alpha stars. Okay, these are the parameters describing their probabilities. So there's going to be an alpha star 0 up to, and remember should be one of these. Let's just write it like this first. So these are going to be, I'm going to write, these are going to be the probabilities of getting class 0. This is the probability of getting class k minus 1. We're going to have this property that they sum up to 1, obviously. And of course, this should be probably different if you have a different input. Like if it's a different picture, the probability you predict each of these classes should probably change. So these parameters should probably be a function of x. Right? And okay, let me just formally remind you of how this works, right? So the way this categorical distribution works is like the probability that y equals to 0 given some xi is equal to alpha star of xi. And dot, dot, dot up to the probability that y equals to the class k minus 1 is just alpha star of k minus 1. It's just literally a table of lookups. So it's like if you have k classes, just assign a number describing the probability of each class. And we give this the name categorical distribution. And of course, the other property is that this thing needs to sum. If you take all the classes, so like y, class y equal to 0 up to class k minus 1, well, if you take each one of these probabilities, they should sum to 1. Okay, okay. That should be nothing too brilliant there. And sometimes we'll call this whole thing now a parameter vector. So this we'll just sometimes write as alpha star vector. Okay, maybe not alpha star vector, but just alpha. Okay, alpha star, if it takes in this vector and there's no subscripts, this will be a vector. And these are indexing that vector. Good. And okay, now we're left with this choice, which is at the end of the day, what is going to happen? We're going to need to somehow learn these parameters. Because if we, okay, in other words, we want to learn this thing. Well, we assume that, each one of these random variables has this distribution. And now all that's left is to find what are these parameters. Because I'm telling you, there are some underlying parameters that will, that govern the probability of getting each label. You have no idea what they are. You have this data. And as we've seen before, like somehow we need to learn these parameters. And to learn these parameters, we're going to minimize this likelihood, this negative log likelihood thing. And to solve the minimization problem, naturally, we're going to want to, pick some function to represent this that's based on some weights or something like this that you can optimize over. And before, remember, we chose the sigmoid for like when there was just a single parameter describing the probability of 1. The question is, what is the function we're going to pick for these? Okay, it should be a function of some weights that we're then going to optimize over. And so what should that function be? And let's just build it up from scratch, I guess. I'll do this in blue, which is, okay, so maybe you want to start with something like this. So you'll be like, okay, the probability of, let's say, class y, right, based on some feature xi. Well, Okay, remember we started for the binary case with, why don't we just try the only function we kind of knew before, which was xi transpose w, right? Okay, and that was all maybe okay at the beginning, but then we're like, oh, this number, this can be negative or positive, up to negative and positive infinity, any number between that, any real number. And we're like, well, that's kind of weird because first of all, we know this probability should be between 0 and 1. So then we squished it between 0 and 1 using the sigmoid. And we can do that for each one of these. We can just say, oh, they're all sigmoid functions. But then that's going to be a little bit odd because then you're going to kind of end up solving up like solving for the probability of each one of these, but it's not going to guarantee this property that they all sum to 1. Okay. And so the way to do this is, okay, you could just you could then, sum them all up and divide by their total sum, which is called normalizing, and achieve this goal. But before applying the sigmoid, we're going to do that kind of first and view it in this other way. So, okay, so this gives you a number. And if you want it to sum up to 1, the natural way to do this is to just normalize by the sum or the prediction of all the other classes. Okay, so in other words, if you take all the other classes, okay, we're going to define, right, since this is for class y, we're going to have a weight vector wy for that class. And so for each class, you're going to have a different function, right? We need a different parameter for each class. So we're going to have a different function. So that means we're going to have a different weight vector for each class, right? Y is between 0 and k minus 1. And so then if for each class, these are probabilities, if we would like them to sum to 1, the natural way to do this is to, well, take the total sum and then divide all of them by that total sum so that when you take the sum, that equals 1. Okay, so in other words, if you take the sum over all the classes, and here to not mix up y, and the sum, I'm going to use q to indicate from q equals 0 to k minus 1 of this thing, which is our like predictions, let's say, using this linear function for now on, or for the time being, to predict things. And yeah, so this number is now some number that's between 0 and 1. And if you were to take this thing and sum over all y, you would get a number that's exactly equal to 1. You would get this, because the top would just become this sum, and then it equals to 1. This is the natural way to normalize things. Okay, so all we're trying to do here is just achieve this fact that it sums to 1. But now it's kind of weird because each one of these well, okay, now it's actually reasonable. These predictions are now a number between, they're less than 1, right? But the problem is that these numbers can be negative or positive. And so it's kind of weird because now you can end up with the probability being a negative number. Okay? And so all that we really need to solve this problem now is to somehow convert this number that's always negative, it can be negative or positive, into always a positive number. And then the kind of way to do this is to just map it through the exponential function. So people will do this. So this is the exponential function will always give you a positive number. Okay. And so then if this is your prediction of getting label y, well, we don't want it to be any positive number. We want it to be between 0 and 1. So then we are going to normalize by the sum of all the predictions. So then you have this exponential down here as well. Oh, and this y, well, this is q. Hopefully that was clear. Okay, so this procedure of this is hopefully motivates this this function here. So this has a name now. This is called the softmax. And really all we did was that we ensured our predictions are positive numbers that are then normalized or scaled into the interval 0 and 1, and that they all sum up to 1. So if you just take the sum of this over all y, you will literally get this denominator in the numerator again, and then it just divides itself and becomes 1. Okay, so this is the softmax for like a particular label y. And if we want to talk about for instance, okay, so this is what we're going to want this thing to be, this alpha star, and we're going to represent it as the softmax. And what notation are we going to use for the softmax? Well, here's a place where, the notation could have probably been better, but we're going to abuse notation and we're going to reuse the sigma. This is commonly used, actually, And yeah, so we're going to use the sigma thing, but the way you're not going to get confused by notation is by the input, hopefully. So based on the input, you're going to know whether this was a sigmoid or a softmax. And so for the softmax, this function will clearly need to know all of the weights, right, to be able to normalize by them. And so this will actually be this function that takes in a bunch of arguments, so not just xiw, but it'll take all of the xiw linear functions. Okay, so let me just move this down so that you can see. So this will be a function that looks like this. It will take in xiw0 up to xi transpose wk minus 1. Okay. So unlike the sigmoid function, it actually takes in a bunch of these, well, takes in k values. Okay. And yeah, and then it does this calculation. Okay. And this is going to be called sigma of y, because this is the y-th label. Okay, good. Yeah, so this is our softmax function. And hopefully it makes sense that we had to move from the sigmoid to the softmax because we want this thing to sum up to 1. And maybe I can also make it clear, this thing is an element of 0, 1. Okay. Yeah, and someone online is asking, why is normalization needed here? And the reason normalization is needed is so that you get a number between 0 and 1, but also when you take the sum of all these, you get 1. So if you take the sum of, well, if you take this whole sum, you get 1. And maybe we can do that. So the procedure for that is the following. Well, actually, let's just do this. Let's take this thing that I've been talking about over here, and let's just prove that it's 1 with one simple calculation. So I'm claiming this is 1. So what is this thing? Well, I'm just going to plug in the definition of it. So this thing is equal to, well, it's the sum of these, right? And then just take the definition of this thing. So let's do that. That's that. Okay, we get that quantity. Maybe I'll move it for one more step. And how does this work? Well, the way this works is that the sum is over y, and y is only in the numerator. And so this quantity is the same as moving the sum to the numerator. And maybe I'll make some more space. It's like this thing. And hopefully you can see that that is just the exact same quantity as below, except at the top you're summing over y, at the bottom you're summing over q. And so you get a number of 1. And the reason you want to do this is because, well, the probability of some class, it's like you should assign some probability to each of the classes and they should sum up to 1. And that's because and okay, maybe one thing to clarify is this multi-class thing is specifically the setting where you believe it is one of the labels. And it cannot be multiple labels that are correct. In the case where there are multiple labels that could potentially be correct, it actually is reasonable to use sigmoids for each thing. Because there you just want to be, what's the probability of this thing and what's the probability of this one? And this is the case where like you would have pictures where like there could be a cat and a dog in the picture. And then you'd like to actually output that there's a cat and a dog. And so, yeah. Okay, so we're specifically focused on this case where there's only a single label that is correct. And that's why we do this kind of procedure. Okay, so after doing all this, what we now have is a representation for each one of these parameters based on some weights. And these weights should all have a star on them because these are the true weights representing the true parameter. And in the binary case, this was just the sigmoid function. Here we use the softmax. All right, now we just need to solve the maximum likelihood estimation problem to estimate these parameters. And then we're done. So how many parameters do we have? Well, we have k parameters, right? There's one parameter for each label. There's one parameter for each labels. There's k of them. So let's solve for them. And do MLE for that. So how is this going to look? Let's just start the procedure on a new page. The procedure is going to look as follows. So there's a lot of parameters now, right? There's like we want to solve for W vector MLE. This is what we used to write before, but in the binary case and in other cases. But now there's like one for the 0th class, and then there's a W MLE for the first class, and up to W MLE for the k-1th class. Okay. And okay, so we end up with having to solve like k of these problems. Another way to view this is that this is just like some giant vector that's all these stacked together, and you solve for it once. Okay, so let's just work through the steps, and then we'll see what I mean. So how does this whole MLE thing work? So the way this whole MLE thing works is we need to minimize the negative log likelihood. So let's just write that right away. So we're going to minimize, and take the argmin of, and I'll write what we're minimizing over in a moment, of the negative. Remember this, you take the log of the likelihood thing, and then it becomes the sum. So over all the data points, it's a negative sum of the logs of this P of yi given xi. And it's based, and before we used to write W, and we used to write like W over R d plus 1, something like this, right? But now we're going to have k of these vectors that are each dimension d plus 1. Because once again, if we recall, for each class, we need a vector, and each one of these vectors is an element of Rd plus 1. And this is the weight vector. And so you have a different weight vector for each class. We just need to find k weight vectors. So now this is no longer going to be like this. It's going to be, instead of just the W here, you're going to have a W0 up to WK minus 1. And so you're going to minimize over not just one W, but W0 up to WK minus 1. And each one of them is in Rd plus 1. And so this notation is not saying that, the whole sequence is in Rd plus 1. It's saying that each one is in Rd plus 1. Instead of writing like this thing for each one separately, this is kind of common abusive notation. Okay, so hopefully this still makes sense. We can see that really the only difference that changed is now we're solving for k weight vectors instead of a single one. And this equation is still just like we've seen before, except now it is based on these k parameters, or k weight vectors. Okay. So how does this work now? Well, we just need to plug in the definition of this and work out the math. That's all we need to do. And so what does this look like? Like, what is this thing? This is the probability of class yi, right? Yi is like some label that you got in your data set. What is the probability of that? Well, this is the assumption, right? The assumption is that the probability of class, well, okay, there's somewhere in here like some other class y, whatever, equal to something, whatever yi is. Let's say yi is, for example's sake, let's say yi in the particular I is like y equals 0. Well, then we know our assumption is that it should be equal to alpha star of xi. And our modeling assumption here is that alpha star of xi is described as the following expression, right? This thing here. And the thing we don't know is w star, and so we're going to replace w star with w, just the w vector we're minimizing over. So we're going to replace this w star of y with w vector of yi now. That's it. So let's just take that. And yeah, we can do it in 2 steps. So we can first of all, it's this function, then we'll plug in what it is. So we just have the same minimization problem. And now we're just going to plug in that probability of the class. And I'll probably at this point make things a little bit smaller to fit. Okay, so we remove this and we plug in the definition of the function, which is this. And this is now yi, right? So for class yi, we pick out alpha star, our estimate of alpha star of yi. Okay, now we plug in the definition of this softmax. Okay. Great. And then at this point, it's just a matter of really solving this minimization problem. And people will just directly try to like take derivatives of this thing, and other people will simplify it a little bit and do it. So we're just going to do one more step to simplify. But at this point, you really just need to take the derivative of this and try to set it to 0, and we're going to find out there's no closed form solution, and we're going to do gradient descent. But all we have is a minimization problem, right, over a bunch of weight vectors. And the way to interpret this, here's another. Okay, so first of all, let's do one thing, which is let's do the simplification step, one more simplification step, and then we'll talk about this being a function. Okay, so all I'm going to do is apply a log property, which you might remember. There's like the log. Okay, I'm not even going to state it because it's we've seen it before. It's like the log of the product of two things is the sum of the logs of those things. What are the two things being producted? Well, it's this times 1 over this, right? So I can replace this with the following expression. Oh, actually, I do need the log property. So there's the log of A over B is equal to the log of A minus the log of B. So you take the denominator and you can actually plug it in as the numerator, but taking the minus sign. Which we could have, okay, I'm not going to waste more time on this, but okay, so you have this. It's just a property. Every time you have like products or division in a log, you can simplify things, basically. And okay, so you have that first term, and then you have the minus log of this term. But I'm going to, okay, well, actually, I'll keep it. So you get that. And then that's all inside the sum. And then we make one more observation, which is that the first term is a log of the exponential function, and we know what that is. The log of the exponential is just the inside, right? So these cancel out. Okay, and now we're in good shape to write out what is the actual function we're trying to optimize over now. And hopefully outside of all this math that you should probably sit down and work out on your own, and again, at some point, you see that all we're doing is just some mathematical steps trying to optimize the negative log likelihood, which we've just written down from the beginning. Okay, and now what's left is to optimize this function. Okay, so now there's a few things to do, which is first of all to give this function a name as before. Now, okay, maybe I'll write it below. So this used to be called like g of w. But now we have a bunch of w vectors. So there's going to be g of multiple vectors. And it turns out that you can show that this is also convex, which is great. Also, it's also in part why we choose some of these functions. So we end up with a convex objective that we need to minimize. And if we find its minimizer, that is indeed going to be the global minimizer. And we will have solved our problem. Okay, some other things to say. So like how to interpret this whole thing where we have a bunch of weights. An alternative, which is like equivalent to this, is that this is a function of a bunch of these things, right? In other words, you could technically create a new vector, which we will just call w, where I'm going to maybe erase it, but this w vector can just be like all these concatenated as one big vector. So that would be like, let's see how you draw this. You can think of it like this visually. So this is like a giant vector where you take the W vector and it takes up maybe this much room. And then you take the W1 vector and it takes up this much room, and you stack them all together up to WK minus 1. And you get this giant new vector, which is all of them vertically stacked. And maybe I should put transposed, which means you vertically stack them. No, we don't need this, sorry. Okay, forget about that. So yeah, we vertically stack these, and what is this? This is now going to be an element of R of, well, it's supposed to be D plus 1 for one of them, but now since we have K of them, it's R of D plus 1 times K. So you can think you have this giant new vector, and then you have this function that's a function of just this giant new vector. And this vector is this, well, it has now K times D plus 1 dimensions. That's fine. We know how to optimize over these kind of, like, it's just a bigger vector. And so now we're going to need to take derivatives of this thing for every one of these dimensions. Okay? And so what you could say is we're going to take derivatives for every single j that's an element of, 0, or maybe I can write it as like 1 up to d plus 1 times k. And you can do it like that. And that's what we were doing before, except we didn't have this k. But that turns out to be a little bit ugly, thinking of it as just giant stack thing. And it's better to just think about like taking it of each one kind of individually. So having two indices, one index saying which class weight vector are we picking, and then within it, which index are we picking, okay? So there's k weight vectors. So we're going to use an index for that. And then we're going to use another index to indicate which index within that class we're picking. Okay. So let's go ahead and now compute these derivatives and stuff. So what we're going to want is to compute something like this, which is the partial derivative of this g function with respect to the w vector and for some class y, right? And then it's at an index j. And then here j will actually be, as we have seen before, which is from 0 up to d. Okay, so this is the index of weight vector for class y. And before, we didn't have this index y. That was the only difference. Now we have a bunch of weight vectors, as many as there is classes. That's really what I'm hoping to emphasize is the difference now. And so we need to take that. And so the way we're going to do this is we're going to break it up into a bunch of chain rule steps. Okay. And maybe for the sake of time, I will leave this as an exercise that's in the course notes that you can see and do. Let's just, I'll give you the solution thing so that we can move on, because I know you need this for the assignment. And then if we have extra time at the last few minutes, we can go through some of these steps. So we're going to break this up into a bunch of chain rule steps. Okay, maybe I put here like see course notes. But we've seen this before. It was like, you define a bunch of like new terms, like you give this a name like UI or something, and then this is exponential of some other thing. Maybe that's a VI, and then this whole thing's like an RI, and then you take a bunch of chain rule steps, and you take these partial derivatives, you piece it together, and you get this equation. And like, what is it after you see the course notes? Well, you end up with the following expression. So this partial derivatives ends up being, unsurprisingly, there's a sum, right? The sum stays, no surprise there. And then what happens with the inside? Well, that shouldn't be too surprising either. So it's going to have a form, which maybe I'll write. Okay, there's not that many steps actually, but I'll write some intermediate point of it, and then we'll simplify it. So it will look of this form, which is that we've seen this like xij thing before, right? Because when you take the partial derivative of this linear function, oh, and the thing I should clean up here is that all these places, this should not be w star, of course, right? Because we are trying to solve for this. And all these y's should be replaced with yi, yi, and yi. Okay, good. Okay, great. So remember we saw this like xij thing before for this type of a function's derivative. There's going to be something in front of it in a moment that I'll write. And then the other kind of quantity we saw is that it ends up looking something like let me just see. Yeah, so here this would have been like something like yi, if you remember. And we'll replace that in a second. And then here you saw something like the predictor. And we were taking the difference. And maybe let me write it in. Yeah, we were taking the difference. And this would have been like the predictor we use to predict things times xi as well. Okay. And so what was the predictor we're using? Well, the predictor we're using is this like sigma thing. So we could literally put this here. And before it wasn't so complicated. Before it was just like this thing or something like that. And then this thing was also multiplied by xij, which we then factored out. And that's what our derivative kind of looked like before. They're going to turn out to have like a very similar form like this. Except now there's just one, like, I guess, caveat here. Which is, okay, so this is going to be for index y, which is matching this thing. And now here, if we look at this derivative, well, this guy here, oh, okay, this is looking, okay, so this is for wyi. So yi, right, can be any one of the classes. It can be any one of the k classes. And we want to take the derivative with respect to class y. So some number. So suppose here I pick 3. Okay. And let's suppose yi was like 2. Well, then this quantity has this weight vector would be for the weight vector for class 2. And if I take the partial derivative with respect to class 3, this term would have nothing to do with it, right? It would disappear. So only in the case where yi equals to the index, which we're taking a partial derivative with respect to, and maybe I should put this here too, which is, so j goes from 0 to d, y is going from 0 to k minus 1. So only when this index we pick for the partial derivative, which is like picking a very specific w in here, you know, only when you pick that specific index, when it matches this, are you actually going to get a term that's non-zero. Okay. And so there is a notation for this function, which is like the function that equals to 1 only when it matches a particular input. And you may have seen this before, and this is called like the indicator function. And so I'm going to define it after I write it down. So we're going to have to replace this thing not with y, but with the indicator that, and the subscript is like a set. And the way this works is that this is a function of y, which is this index we're using here. And so only when y equals to this is this function equal to 1. Otherwise, it's equal to 0. Okay. And similarly here for this sum, what you will find is that it's only going to be interesting in the cases where q actually matches y. And so in that case, you will just end up with this single quantity here, it turns out. And so that's why you have a y here as well. Okay, when you go through the course notes and these steps, maybe that will show more steps. Okay, so you end up with this kind of expression, and just for definition's sake, the way this indicator function works is it's the indicator, you put a subscript, a set, and it takes in as input little z, and this function is equal to 1 if z is in the set and 0 otherwise. Okay, so this is, instead of having to write this like piecewise function thing, it's nice to have some sort of like common notation, and this is commonly used. So if you want a function that equals to 1 on some set of values and equal to 0 everywhere else, this is how it's done. And yeah, and so this set could be larger than just one thing, but for our case, we just need it to contain one element. Okay, and once we see this expression, we can simplify further to get the following, which is we can factor out this xi. So I'll just delete this guy, take this guy outside. And we end up with an expression like this. Okay, and there should have actually still been a negative out here. There was no reason that negative should have went away if you do the derivatives. And what you'll now, if we expand this negative inside, these negative will become a positive. There'll be a negative here, and so these things flip. Okay, so we end up with an expression like this. Which is something we've kind of seen before, which is like this xij is outside. You now have your predictor, and you're just comparing it to the actual label. And now you have to do this extra checking of whether it's actually the class yi or not for the index you're looking at. Okay, so that is a pretty similar form to before. And so that turns out to be the derivative. And once we have that calculated, we can then try to set this to 0. But unfortunately, no closed form solution exists. And so then we have to do gradient descent using these kind of partial derivatives when you plug them into the gradient. So you use gradient descent. And so gradient descent will look like this now. And you're going to have to do gradient descent over this giant vector, right? Which you can break up into doing it for each one of these separately at each iteration. And so we're going to write it out in that way. So we'll write it as the gradient with respect to one of these classes, weight vectors, wy, of this g function. Well, that's going to equal to this del g of del the derivative with respect to wy. And then the thing that's new, right, is having this y here. But before we had this y, it would have been like at index 0 up to derivative g with respect to y at index, well, there's d, right? So, wyd. And as before, this is just an element of rd plus 1, as every gradient we've seen has been. And the difference is you're going to have this gradient for every single y that's in our set of classes. So I've written y is in the set of labels, right? There's 0 up to k minus 1. And then the way gradient descent works is now you're going to take gradient steps for each class y of our weights. And so the weight vector at step t plus 1 is going to be equal to the weight vector at step t minus the step size at step t times the gradient, which we just calculated, of wy vector of g. Where you've plugged in here, you're going to plug in the weight vectors you've calculated at steps t, at steps t, and you're going to do this for all k minus 1 classes. Okay, so before this thing used to just have one weight vector because there's only one class or one function we had a weight vector for. Now you have k of them, k minus 1, and this function will still be a function of all of these, as we see above through this. So each partial derivative is still a function of all these weight vectors. Okay, and so you would do the way this procedure works is, so for each, for each step, so for each gradient step t, you do the above calculation or step for all y in y. So in other words, when you're implementing this kind of thing, what you do is you do all of these steps, like for all y's, and then you go to the next iteration. So there's an outer loop which is going over iterations until the last epoch, capital T. And within that, there's an inner loop that goes over all the classes and does this update k times. And all you're doing is just simply, instead of updating this whole weight vector at once, this giant thing which is that we've stacked together, you're just breaking it up into a bunch of individual k updates. So you could have just stored the whole thing as a giant weight vector and done it all as one update. Or it's just nicer kind of to think about as doing k updates at each step. What you don't want to do is update each weight vector capital T times that do T iterations and then move on to the next weight vector and so on. What you really want to do is that, simultaneously update all the weights, which is kind of your estimates of each of the probabilities of the k classes, and then do another step, like one at a time. So you want to update all your estimates and then do a step, and then update all your estimates and then do another step. To basically resemble the procedure we've seen for gradient descent, which is you have one giant weight vector and you update it one step at a time. You don't randomly update some subparts. That would be kind of the equivalent where weirdly you update like W00 like T times, and then you move on to W01 T times. That's not what you want to do. Okay, so that's the procedure for running this. And the predictor, the way this looks, is as follows, which is the learner. So we have this, so it's the multi-class classification learner. And it's just going to be through this approximation of f-Bayes using the predicted alpha stars, or the predicted parameters we have just gotten. So that is actually very nice and simple. You just start with this. This was our goal. We now have an estimate of this. How do we have an estimate of this? We have an estimate of it because for each value of y, we claimed, right, for each value of y, it's just alpha star. And now we have an estimate of alpha star, which is this function with the MLE estimates plugged in. Okay, and so that's going to look like this. We're now going to say this is approximately equal to our estimate of the PMF. What is the estimate of the PMF going to look like? Well, it's just based on these MLE estimates. And so, of course, we don't get like the perfect MLE estimates because we're doing gradient descent, but we'll get something quite close. And so the learner here is going to be based on these. And once again, you can't quite get these exactly, and so you should be replacing these MLE things with your actual solution of gradient descent. So you'd get another extra error there. And then afterwards, well, okay, so that's what that is. And then I can just remind you, what is this function? This function is simply that softmax that we have up here. It's just this thing, but with W star replaced with WMLE. This was just by assumption. So all I'm doing is taking these W stars and I'm replacing them by the MLE versions of them. So this is MLE, right? Our estimates of W star. That's it. And that will be our predictor that we get based on data called F multiclass. We had this F hat binary before, now it's F multiclass. And so our learner will simply, what it will do is it will take in the data set and it will output this thing. And the way it uses the data set is through calculating these maximum likelihood estimates of the weights, right? Because to solve this problem with gradient descent, it requires data. And where's the data? It's like these xij's and these yi term here. Okay. Yeah. So that's the learner. And now what we'll do is we'll see that you can equivalently think of this whole MLE story as just solving a regression problem and then just picking the class that has the largest probability. So we've already seen how, okay, we're already seeing that right here. You solve for the, like, what is this? This is just the probability of class Y, and you're just picking the argmax, the class with the largest probability, based on your estimated probabilities. So this procedure of estimating the probabilities for k classes can be thought of as a regression problem, where you're estimating the probability of k different targets, labels, which are all numbers between 0 and 1. Okay, and that has a name, which is called softmax regression. And maybe before getting to that, I wanted to just quickly draw a picture of how this whole thing can be thought of, which is that basically this procedure, similar to before, can be like our predictor can be thought of as creating these decision boundaries, which in these regions to the sides of the decision boundaries, it predicts a certain class. So if you had data of this form, so I'm going to denote with x's class y equal to 0, with circles the class y equal to 1, and with triangles the class y equal to 2. And maybe you get data of this form. And then you get some circles. So these are, and of course these are the features, right? Like you have two-dimensional features. So there's x2 and x1. And that's just because we can't draw higher dimensions. Something like this. And then there's some triangles. And so it turns out that in this region of the features space, you get these labels of 1, 2, and 3 as follows. Okay, fine. Maybe that's what it looks like. And so it's like, oh, in this region, it seems I'm getting the label 2. In this region, it seems I'm getting the label 0. Here, maybe I'm getting the label like 1. And so what will your predictor do? Well, if I give this like the color kind of purple, and I give this the color blue, and this the color orange, well, then maybe this kind of area I should predict 0. And then maybe this kind of area I should predict 1. And then here, okay, maybe I should predict 2. Right? And in other words, maybe like the class with the largest probability should be the class 1 here, or the class with large probability should be the class 2 here, or sorry, 1 here. And the class with large probability should be the class 2 here. So class 0, class 1, class 2. And so naturally, there's going to be a point at which there is a change between this being the largest probability changing to this class, right? And that is where the decision boundary will be. And that is exactly how you can visualize your predictor. It's like, you know, in the purple region, it's predicting 1. In the blue region, purple it's 0, blue it's 1, orange it's 2. And these are the boundaries. And particularly at these boundaries, what's happening is like the probability of y equaling to 0 given an xi based on all these weight vectors is exactly equal to the probability of y equaling to 2 in this case, based on this xi vector, based on all the MLE weights, right? And both of these are a larger value than the probability of getting 1, because it's going to be either this or this. And so that's what these boundaries are. And the reason they're linear boundaries is because we've chosen linear functions here. And once again, you can replace this linear part with a polynomial, and then you can get more complicated looking boundaries that are polynomial looking. And that's how you should think of this procedure, is that you basically output a predictor of this form that creates these decision boundaries. And these are the regions where the probabilities are the largest, these classes, and then you just pick the one with the largest probability. Okay, and then finally talking about this whole view of it as a regression problem. So that would be called softmax. We've seen logistic regression. Well, now we're doing regression with the softmax function. Okay, and the way this works is now there's k probabilities you need to predict. So it's going to turn out to be a regression problem where your labels y, or your targets y, are now not just in, so you're going to have this y, which I call softmax, which are not just in 0, 1 as before, but they're going to be a vector valued target. So they're going to have k dimensions. It's going to turn out the procedure is essentially the same as before, though. And these are representing values, right? These are representing the probabilities of y equaling to 0 given some x up to the probability of y equaling to k minus 1 given x. Okay. And so this is sometimes called multi-output regression. Where you're now outputting a vector instead of just a single continuous value. And so what the labels will look like in this case for this regression problem is, for example, if k equals 3, well then something like 1, 0, 0, so that's the three-dimensional vector, will be for class or for label 1, and then something like 0, 1, 0 will be for like class 2, and these are vectors and legs. So they're just these one-hot vectors that basically have a single one at the corresponding index of where the class is. So that's what your data will look like. Because you have your data is just what's the correct label, and then you will represent it like this for your regression problem. And then it turns out that the loss here is no longer the binary cross-entropy loss, but called the multi-class cross-entropy loss, or they're essentially the same, but sometimes written slightly differently. And so the loss for like a y vector now, instead of just the y, so normally it would be like y hat compared to y, but now they're vectors, is written as follows. It's like -1, and then you take the sum from your classes k or q equals 0 to k minus 1 of the corresponding y, which is the correct label, at its index. And what index do you pick? You pick index q, and you multiply that by the log of y hat at index q. So that's your prediction of the probability of that class q compared to what is the actual correct probability of class q. And this turns out to be exactly equal to, but I don't have time to make it clear, is exactly equal to this expression if you look at it from here. Because essentially, this has this log. This is your prediction. This is your y hat at index yi. And yeah, so if you squint at this for long enough, you'll find that these are actually equal. And then for that reason, your function class that you should pick for y hat is just going to be the set of softmaxes, right? Because we need these vector valued functions, these functions that output vector values. So they're going to be functions from r d plus 1 to the 0, 1, but to the k. So you output k probability values. And the special property is that each one of these is now equal to not the sigmoid, right, but the softmax of these w vectors. Okay, where these vectors or these weights are in rd plus 1. And then finally, the learner is just ERM. So then the ERM learner will look as before. It's just going to minimize. So this FERM is just going to equal to the argmin function in this function class, where now the functions are softmaxes. And it's minimizing L hat of F, where L hat is based on this loss, which is the multi-class cross-entropy loss. And then it turns out that if you look at this, the only difference between the minimization problem from before and ours is that this quantity, when we write it out as the sum I equal 1 to n, is it'll have a 1 over n term. And if you remember, that doesn't change the minimizer. And so this will be exactly equal to FMLE, we will find. which is like, we should call this thing FMLE. So it'll just be exactly equal to this solution. And so that's the equivalence of like regression with softmax regression with the MLE approach. Okay. And yeah, and so you would just take to solve for this, right, you would take the derivative of this loss thing, which turns out to be the exact same procedure as this thing we've done above, except the only difference is that you will have this like 1 over n over here in the argmin thing, because you have this average that we've seen before. And I think you work this out on your assignment, but that's the story of multi-class classification. And I guess I will, actually there's one last point, which is that you might have this question about what is the relationship between multi-class classification and logistic regression, or softmax regression and logistic, and it turns out they're equivalent, but you need to do a little extra work to check that that their predicted parameters, these alpha stars and alpha 1, alpha 2 star, whatever, are the same. And that also, the course notes go over that if you want to look at it. Okay, I ended here.